Hey guys, and welcome to lecture 2 of our electrical engineering series. In this lecture, we will be talking about standard notation, which is expressing large or small numbers in readable form. Now, you might be saying, what is the use of this in electrical engineering? Well, I will tell you that electrical engineers use very, very large numbers and very, very small numbers in tandem very, very often. Now, a lot of numbers in electrical engineering are orders of magnitude apart. Take this, for example. Let's take a look at time. So, your clock. The second hand is basically a 1 Hertz clock. Every tick happens once every second, and we define that as a Hertz. Now take a look at the Intel Xenon chip. Now its internal clock is somewhere between 3 to 4 billion times per second. So to put that in a visualization, every time that clock secondhand ticks, the Intel Xenon's clock would have ticked 3 to 4 billion times. Think about that for a magnitude difference. And just because of that, we have to figure out a way to represent both extremely small values and extremely large values in a holistic notation. Welcome to standard notation. Now there's two types of standard notation. There's scientific notation and there is engineering notation. Now they're both very, very similar. Scientific notation takes the form of this: a one-digit number multiplied by 10 to the power of something. It can be positive, it can be negative. That's scientific notation. Now this is definitely more intuitive of a representation than engineering notation. But in engineering notation, it's actually even simpler. You find the one-digit number, base number, like you did in scientific notation, but instead of multiplying it by 10 to an exponent, you put an e after it, and then you put the exponent number. Now this is much cleaner than scientific notation, but in some cases maybe less intuitive. But these things are so similar, you can switch them in a blink of an eye. And so that's why I'll teach them to you at the same time. Alright, so let's take a look at an example. Now, remember how to express scientific notation. You first have to find its base number. So how do we find that? Well, let's start from the left and make ourselves forward through that sea of zeros until you find a non-zero number. In this case, our savior is the 6. Now, put a dot right after that 6. That 6.432 is your base one-digit number. Now, you take that dot which you've placed, and then you notice the original dot. Now, you take that dot and you just move it to the next place and keep on moving it like a little bunny until you get to your original decimal place. Now, don't forget to count because that's crucial. In this case, we moved left 13 hops. These two things, the direction of travel and how many hops you made, is very, very important to how you express it. In all cases, moving left to your original decimal place means that your final exponent has to be negative. Now we moved it left 13 hops, so that's your exponent. So 13 hops becomes negative 13. And then you take that negative 13 and you shove it right onto a 10. So what do you get? You get 6.432 times 10 to the negative 13. And bang, you have got your scientific notation. Let's take a look at a different example. In this case, this number is huge. Now, our approach stays pretty much the same, except in this case, your base case will actually start at the beginning if you don't have any of those weird leading zeros. So our first non-zero number is, well, 5, because going from the left, your first number is a 5. So to find your base case, put a dot after that 5, and then find out where your target decimal place is, which is actually after the end, which is after the 8. So you make those bunny hops from your temporary decimal to the actual decimal. In the end, you will get 15 hops going to the right. That means your exponent is going to be positive. So you take that 15 hops and you place it right on top of a 10 as the exponent. So you get this giant decimal, 5.63 ... times 10 to the 15. So let's take a look at how to do engineering notation. Now this is the same as scientific notation, plot twist, except, as I've said before, just have to put an e and the exponent. So remember this number, we don't have to do the math because we've already done it. So we have this number. What do? We put an e after the 6.432, and then put the negative 13 after the e. It will look something like this. And there you have it. You've got your engineering notation. That's how simple it is. Alright, so we know how to express things in scientific notation and engineering notation, so how do you turn something like scientific notation into what we call layman's terms, which we hear of every day? Ever heard of a terahertz, or a gigabyte, or a megabyte? Well, you have, because those are standard computer terms. Now, what you might not have known is that these actually represent scientific notation. Every multiple of 3 on the exponent can be represented with a layman's term prefix and a symbol. So, take for example, we had 6 times 10 to the power of 12 hertz. Well, we can represent that by 6 terahertz, which is actually really, really high. In writing, we can say 6t, capital T, Hz. Now, any numbers, multiply them by a positive magnitude of 10, those symbols are always uppercase, except the lonely guy here, kilo. Kilo special. You have to do a lowercase for some reason. Now, every single small magnitude multiplication, like 10 to the power of negative 3 or 10 to the power of negative 15, those are all lowercase. And micro is a little bit of a special kid here. It is not a standard character, but it's actually a U with a little tail on it. That you have to be careful, but everything else is very intuitive. So now we know how to express both large and small numbers. But what do these numbers actually represent? Well, we will have to find out in the next video. See you then.